Hey everyone, let's dive straight into this explainer and become full-fledged data detectives today. We are going to solve the mystery of what exactly happens when massive amounts of mathematical data are hidden inside groups. Just imagine looking at a massive grouped frequency table, or maybe a totally blank grid for a cumulative frequency curve, and needing to extract the absolute truth from numbers you can't even see. It's like a giant puzzle, and today we're getting the pieces to solve it.
So the crucial point here is this core question. How on earth do we find the exact average when the actual numbers are completely hidden from us? When we look at grouped frequencies, those individual results are just lost. The raw data is completely gone. We need a specific toolkit to figure out what the data is really trying to tell us. Because when continuous data is grouped like this, we have to make a logical, mathematically sound assumption to move forward.
Here's our roadmap for the statistical tools we'll be mastering today. We're going to start with grouping data effectively, move right into estimating the mean, construct the cumulative frequency curve, track down the median, calculate the quartiles and the interquartile range, and finally, wrap it all up with a battery showdown.
Let's kick things off with Section 1, Grouping Data Effectively.
You know, out in the real world, data is just messy. If we recorded the exact running distances of hundreds of students, looking at all those numbers would be totally overwhelming. So what do? We group them into class intervals. But there's a definite trade-off here. We gain a ton of clarity on the overall shape of the data, sure, but we sacrifice knowing the precise individual values. For example, we know exactly 8 students ran somewhere between 270 and 279 meters, but their specific individual distances completely hidden from us. Did all 8 of those students run exactly 271 meters? Did they all run 278 meters? Or are they just spread out evenly? We simply don't know. The raw data is locked away for good.
Moving on to Section 2, Estimating the Mean. Since those exact numbers are hiding from us, getting a perfectly exact mean is, well, impossible. But don't worry, we can mathematically estimate it using a really specific, clever procedure. By assuming all the data within a group takes the exact middle value, like using 274.5 for the 270 to 279 group, we can calculate a highly accurate estimate. Step 1, find the mid-interval value by averaging the lower and upper boundaries of the group. Step 2, multiply that mid-interval value by the frequency. That gives you an estimated total for that specific group. And step 3, add all those totals together and just divide by the total frequency. It's that simple.
When we follow those exact steps, it gives us an estimated mean running distance of 282.5 meters. By laying out our mathematical logic, multiplying our mid-intervals by our frequencies, summing the whole thing up, and dividing by the total number of students, we prove that we can bridge the gap. We can find a super reliable average even when the raw data is completely missing.
All right, Section 3, the cumulative frequency curve. Now, an average is absolutely fantastic, but it's not quite enough when we need to measure consistency. The mean is a great center point, kind of like a balancing act for the data, but it hides the extremes. I mean, what if some runners were incredibly fast and others were practically walking? To truly analyze this spread, we need a cumulative frequency curve. Think of the word accumulate. You're basically hoarding the data as you move through the classes by progressively adding the frequencies together. If the first group has 3 people, your cumulative frequency is 3. If the next group has 5 people, your cumulative frequency becomes 3 plus 5, which is 8. And here's a pro tip. The final cumulative frequency must always equal your total sample size. It's a built-in safety net to make sure you're on the right track.
Let's bring this into the real world with a test of 50 Type A batteries versus 50 Type B batteries. We're tracking their cumulative durations up to 35 hours. Notice the notation here, right? Time is continuous. It doesn't just stop. In this data, we've already done the accumulating. By the 15-hour mark, 16 of the Type A batteries have died, compared to only 12 of the Type B batteries. By 25 hours, 38 Type A batteries are dead, while a massive 44 of the Type B batteries have failed. We're dealing with a total sample size of 50 for both types, which gives us a truly perfect basis for comparison.
Okay, to actually visualize this data, here's the golden rule. You absolutely must plot your points at the upper boundary of the interval. So, for instance, at exactly 5, 10, or 15 hours, you have accumulated all the data up to the very end of that interval, so you plot the point at the upper boundary, never the mid-interval. And then you join them up with a smooth, continuous curve. A cumulative frequency graph models continuous, real-world phenomena. A smooth curve perfectly shows the natural, flowing progression of the data.
Moving right along to Section 4, Finding the Median.
With our smooth curve drawn, we can officially track down the true middle of our dataset. The cumulative frequency y-axis represents the actual physical items, in this case the 50 batteries. To find the median, we need the 50th percentile, which literally means the 25th battery. We just look at the 25 mark on our y-axis and draw a horizontal line straight across until it hits our curve. The exact moment it intersects, we drop a vertical line straight down to the x-axis. Whatever time that lands on in hours, that's our median. It tells us the exact duration where half the batteries have died and half are still working. It's a way more robust measure of the middle than the mean is, because it completely ignores those extreme outliers.
So, by drawing those lines, we see the median for type A is approximately 19 hours, while the median for type B sits at about 18 hours. This tells us that, strictly on average, type A batteries last 1 hour longer than type B batteries. But hey, remember, the median is just an average. It represents the 50th percentile. It absolutely does not guarantee that every single type A battery will automatically outlast a type B battery. Keep that in mind.
Which brings us to Section 5, Quartiles and the Interquartile Range.
We know type A has a higher median, but wait, does that automatically make it the better battery? Absolutely not. To really evaluate performance, we have to look at the spread using quartiles. Think of quartiles like quarters, cutting the data into 4 equal pieces. A standard range is just the absolute highest value minus the lowest value. But what if one battery was a total dud and died after just 1 minute, while another was an absolute freak of nature and lasted 100 hours? The standard range would be massive, but it wouldn't reflect the normal batteries at all. The interquartile range, or IQR, solves this problem beautifully. It chops off the extreme bottom 25% and the extreme top 25%. It only measures the spread of the middle, most typical 50% of your data.
By checking the 25th and 75th percentiles on our curve, we can extract these exact quartile values for both brands. Our total frequency is 50. 25% of 50 is 12.5. So we draw a line across from 12.5 on the y-axis to find our lower quartile. For type A, it's 13 hours. For type B, it's 15 hours. Now what about 75% of 50? That's 37.5. We draw a line across from 37.5 on the y-axis to find our upper quartile. Type A is 25 hours and type B is 21 hours.
Now, to find that all-important IQR, you just take the upper quartile and subtract the lower quartile. For type A, 25 minus 13 gives us an interquartile range of 12 hours. This number represents the spread of the middle half of all type A batteries tested. Guys, a spread of 12 hours is huge. It means that even among the most typical type A batteries, you could have one die a full 12 hours earlier than another. That is a massive level of uncertainty.
Type B, on the other hand, has an interquartile range of only 6 hours. We just took its upper quartile of 21 and subtracted the lower quartile of 15. A significantly smaller IQR mathematically indicates that the data values are clustered much closer to the median. Therefore, as a consumer, you can expect a much more reliable, highly predictable performance from Type B batteries.
And finally, Section 6, the Battery Showdown.
Now we get to apply all our hard-earned data detective work to figure out which battery is actually the winner here. On one side, we've got Type A, a higher median but a massive interquartile range. On the other side, we have Type B, a slightly lower median but an incredibly tight, consistent spread. This brilliantly illustrates how data translates to the real world. If you're the marketing director for Type A, you're shouting from the rooftops about your 19-hour median, claiming your battery lasts the longest. But if you're an engineer designing, say, a critical medical device, you don't care about a slightly higher average if the battery might just randomly die 12 hours early. You want Type B. You want reliability.
Because Type B's interquartile spread is literally half the size of Type A's, you know exactly what you're getting every single time you pop it into a device. You've officially moved beyond just crunching numbers, you are now interpreting them. You went from raw grouped frequencies, calculated an estimated mean using mid-intervals, plotted a perfectly smooth cumulative frequency curve on the upper boundaries, tracked down the 50th percentile median, calculated the IQR by subtracting the 25th percentile from the 75th, and arrived at a super powerful evidence-based conclusion.
It just goes to show that out in the wild, the average is literally only half the story. Understanding the spread of the data is the true key to making smart, informed decisions. So, the next time you're looking at data, ask yourself, are you a gambler or are you an investor?